recording now.
Good afternoon.
Good afternoon.
My name is Haggai Mwansa. I'll be your chemistry trainer as well. I'm sure for some of you we met last time in biology.
Yeah.
Yes, and we are continuing today, the last little part that we made. Okay, so we are starting with chemistry today. Are you able to see my screen?
Yeah, you're able to see your screen.
All right, thank you. So I'll just run through the introduction of chemistry here. What's written atoms? The start of chemistry begins with the basic unit of matter, the atom. The Greek philosopher Democritus called the smallest fragment of matter the atom, from the Greek word atomos. This is just an overview of the basic chemistry that we're about to get into. Placed side by side, 100 million atoms would make a row only about 1 centimeter long. Atoms contain subatomic particles that are even smaller. So what 3 subatomic particles that make up atoms, or what 3 particles that make up atoms? As you've been told, atoms are made up of 3 particles. Anyone can tell me these 3 particles, subatomic particles, that make up an atom? Any idea? Before I can go to the next slide, just give it a try. Atom. Okay. So subatomic particles that make up atoms are protons, neurons, and electrons. So we can go back and define an atom. Okay, so the basic unit of matter, the atom. The matter is made of a lot of atoms. So basic unit of matter, and that atom is made up of 3 particles. The 3 particles that we are calling protons, neurons, and electrons. They make up an atom. We are moving together. Thank you. Good. Smallest property of an element, that still has the properties of that element, the building blocks of matter. So here they are defining an atom in a different way. An atom is the smallest property of an element that still has the properties of that element, the building blocks of matter. So atoms are actually the building blocks of matter. Atoms make up the matter. They are the building blocks. So atoms are made of smaller subatomic particles arranged in a particular way. Yes. So you're seeing that? That's just a symbol for a proton. Protons are always positively charged. Always. Neurons are neutral. Electrons are always negatively charged. And these 3 subatomic particles make up an atom. An atom, which is building blocks of matter. Okay, so protons and neurons have about the same mass. Before we can go further, just someone to, of us, we understand what we mean mass, right? We're talking about weight or the quantity. So protons and neurons have about the same mass. So protons and neurons, for example, we would know the number of protons. Let's just give hydrogen for it to be asked to say how many protons and neurons do hydrogen have. So they are saying the number of protons and neurons. Protons and neurons have about the same mass. They have about the same mass, almost, not always. Protons are positively charged particles, like I had said earlier. The neurons carry no charge. No wonder there is that sign. It's neutral. So neurons carry no charge. Protons are positively charged. Neurons carry no charge. Then electrons, these are always negatively charged. Strong forces bind protons and neutrons together to form the nucleus, which is at the center of the atom. So they give us a simple structure of an atom, which I think that we'll get a better one, but from this view. This is the point they're trying to get. What actually helps them to bind together is the charges that they have. So no wonder we have protons that are positively charged, neurons that have no charge, and then we have the electrons that are negatively charged. So strong forces behind protons and neurons together. Strong forces bind protons and neurons together to form the nucleus, which is at the center of the atom. The circle at the center of the atom. It's called a nucleus. That bind is made by protons and neutrons together by strong forces. The electron is a negatively charged particle with 1 over 1,840 the mass of the protein. So they're describing an electron here. An electron, which I earlier mentioned, it's negatively charged. Electrons are in constant motion in the space surrounding the nucleus. Electron cloud. Here's something to demonstrate. Okay, so electrons are in constant motion. The way a nucleus is made, it's like a circle. So an atom has rings. It has the first inner circle, which is a nucleus. Then it will have another ring. So the way electrons move, they move in constant motion in the space surrounding the nucleus. They'll be moving around the nucleus constantly. Are we together? Are we together? Just let me know if you're able to get me, please. Hello?
Yes, we are getting you.
Okay, thank you. Thank you very much. Okay, so this is what I was trying to explain. The subatomic particles in a helium atom. This is an helium element that they are trying to extract from here. So protons are always positively charged. Neurons have no charge. Electrons are always negatively charged. So they've shown here. Remember what I mentioned about the atomic number being of the same atomic number being of the same, atomic mass being of the same with the electron number in an element, making up a mass number for that element. So atomic number for helium, they've shown there. I'll soon show you just the table on the screen. It's just a minute. Okay, I'll start sharing soon. I want to retrieve the periodic table so we can appreciate it. And are attracted to the positively charged nucleus. Positively charged nucleus. This is a nucleus which is positively charged. And these are electrons which move in a constant motion around the nucleus. I hope you're seeing that. This is the point they're trying to clarify. Electrons are attracted to the positively charged nucleus but remain outside the nucleus because of the energy of their motion. Because atoms have equal numbers of electrons and protons. And because these subatomic particles, the subatomic particles, which is electrons, protons, and neurons, have equal but opposite charges, atoms that are neutral. I will repeat. Because atoms have equal numbers of electrons and protons, each atom of an element has the same number of electrons and protons. And these same electrons, protons, and neurons, which are subatomic particles, have equal charges but opposite. They have equal but opposite charges. Atoms are neutral. Don't miss this. Neurons have no charge, atoms are neutral. Atoms are subatomic particles, they're the building blocks of atoms. And atoms, they are the subatomic particles, and the neurons, protons, and electrons that we've been discussing. And atoms are the building blocks of matter. So the atoms are neutral. Okay. So here they've just clarified this. Atomic number of a proton and electrons in an atom. Mass number is the total number of, so I say atomic number of protons and electrons in an atom is the same. And what makes up a mass number of an atom is the total number of protons and neurons in an atom. So if you want to find the total mass number of an element, for example, helium, you're supposed to add the number of protons plus the number of neurons, which they actually showed here. Okay, so we have this. So the proton number of this element is 2. And the same number of the proton is the same number for the neuron. proton plus the number. This is the point they're trying. This is the mass number we have 4. This is the point they're trying to nullify. Mass number is the total number of protons plus neurons in an atom. Don't get this mixed up, not electrons. Mass number is the total number of protons and neurons, not electrons. Proton and neurons in an atom. And then they say the number of protons in an atom is equal to the number of neurons. So this is how they came to this 4. Here. Mass number is 4. Proton number is 2. Neutron number is also 2. So 2 plus 2, they are coming to the mass number for an element, helium, which is 4. Number of neutrons, mass number minus atomic number. This is how you find the number of neutrons. They are showing us here. The number of neutrons, the negatively charged, the number of neutrons, which is the neutral ones, the one with no charge, the one we are adding to the protons to find the number of mass. So they are saying number of neutrons is equal to mass number minus atomic number. So if you do not know the number of neutrons, it's simple. But whilst you're given the number of the atomic number. So for example, here we have been given the number, the atomic number, and we've been given the mass number. And then you're asked to find the number of electrons.
Excuse me.
Yes.
Kindly repeat the atomic number. What is atomic number?
The atomic number.
Yes.
It's the number of protons and electrons in an atom. Okay, I would say proton. Okay, the way they've actually described it here, proton atomic number, number of protons and electrons in an atom. So for example, they've shown here, this is an atomic number of helium, it's 2. And when we have an atomic number is the number of protons. Number of protons that are positively charged and electrons in an atom. So atomic number, for example, here they've shown us the atomic number for helium is 2. So if you want to find the atomic number, if you want to find the number of this is what I was trying. This
Excuse me, sir. Excuse me, sir.
Yes.
Excuse me, sir.
Yes, I can
The
get you.
screen
Go ahead.
that you are sharing is the periodic table.
What?
Is the screen that you are sharing is the only the periodic table is what you are seeing on the screen? Is there any screen? Is there any?
Sorry, I don't know if it's your network. I can't get you clearly.
Screen that you're sharing? The periodic screen that you're sharing.
Yes.
If one is just showing the periodic table.
Oh, yes.
You are explaining about the periodic table.
Yes. Before I could get to the periodic table, I wanted you to understand these concepts before we can get there. You wanted to do something. You asked about the atomic number, isn't it? Yes, the atomic number of protons. The atomic number is the number of protons in the nucleus of an atom. Are you there?
Yeah.
Yes, she had a question. I couldn't get it clearly. Talking about the periodic table. Please ask again. Okay, so we proceed. Those who didn't get this one clearly, atomic number is the number of protons in the nucleus of an atom, which a nucleus of an atom has also electrons. So that's an atomic number. So mass number, which explained, we said total number of protons and neutrons in an atom makes up the mass number. Here it's the protons and the electrons that makes up the atomic number. So when you're given the number of the atomic number of an atom, then you also know the proton number. You know your electron number by subtracting the number of protons from the atomic number. Then you will know the number of electrons. Then I was explaining on number of neutrons. How to find the number of neutrons. Number of neutrons, you subtract the mass number, you subtract the atomic number from the mass number, then you have the number of neutrons. For example, mass number, we subtract the atomic number. Here, the mass number, you subtract the atomic number from the mass number to find the number of the neutrons. So ion charged atom can gain or lose electrons. If an atom gains an electron, does it have a positive or negative charge?
So a positive charge.
Come again?
When an ion gains an electron, it has a positive charge.
Does it have a positive charge or negative charge?
Positive.
Positive. Why so?
There is an addition of an electron.
Come again?
There is the addition of an electron.
We want everyone to get that statement, that word.
Because there is addition of an electron.
Yes, so it will be
Positive.
positive charge. Okay, so let's proceed. Does it have a positive or negative charge? What if the opposite is true? You know what we expect when we add a positive to a negative. So lose electrons, it's positive. Gain electrons, it's negative. It's the opposite. So when an atom gains an electron, when an atom, I repeat, when an atom gains an electron, they've explained it in a very simple way. Lose electrons, positive. So the atoms that lose electrons are the positive ones. Gain electrons, negative. Where can okay, so we have something to look at here from what I was explaining. Okay, so this is the carbon. This is carbon. Atomic mass number is equal to number of protons plus neutrons. The number of protons. There you have it. Number of protons is the atomic. So number of protons is equal to atomic number. Then the atomic mass number. These two are confusing because, yes.
Please share your screen.
You're not able to see my screen.
The only thing which is there is the periodic table.
Seriously, I had asked. No wonder. Oh my goodness. Yeah, I'm thinking it's sharing because it's sharing for me, showing me that it's sharing. I had asked to say, let me know if you're able to see. So I thought you'd been, wow, sorry. Let me share again. Oh, this wow. Oh my goodness. So I thought we were looking at the same information. Are you able to see it now?
Yes.
Okay. So I'll just take you through a little bit in this before I can jump to the other part since you are not seeing anything. So atomic number is the number of protons and electrons in an atom. The mass number is the total number of protons and neurons in an atom. The number of neutrons, number of neutrons is equal to the mass number minus atomic number. Then this is the question I asked about the ion charged atom can gain or lose electrons. If an atom gains electrons, please mute your mic. Are you able to get me now? Are you able to get me now? And the screen, is it still sharing?
Yes, we are able to get you.
Thank you, thank you. So the points that we're explaining here, this is the structure to make it easier for your understanding here. So protons, the number of atomic mass is equal to protons plus neutrons. So the number of protons and neutrons makes up the atomic mass. So when you're given the atomic mass without the number of neutrons, but you know the number of protons, it's easy to subtract the number of protons from the atomic mass number to find the neutrons. This is just an equation that rotates in case you don't have any of it. If you wanted the number of protons, you will be protons is equal to atomic mass number minus, because neutrons is going to come inside. So minus neutrons to find the proton number. So proton number, this is the atomic mass number that we have here. It's 12. Number of protons is 6. Please mute your mic. Please mute your microphone.
I think it's name to my microphone.
Please make sure you mute your microphones unless you have a question or anything, so we don't get inconvenienced. Okay. Okay, so we proceed. So I was explaining how you can make use of this simple equation. The atomic mass number of an element is equal to the proton number plus the neutron number. So if you are given the proton number without the neutron number, simple, you just say proton number is equals to atomic mass number minus the neutron. Or simply just subtract the proton number from the atomic mass number. Then what you have is the number of neutrons. Then the number of protons, here, like they have shown here. Number of protons is 6, carbon. Then the atomic mass number for carbon is 12. So we know the neutron number, of course, it's 6 as well, because you're going to subtract 6 from 12. Then what you have is the number of neutrons. Okay, so the atomic number. Okay, now let's solve this one. Oxygen as who can tell me the atomic number of oxygen from that illustration I just gave?
Eight, sir.
Yes, I can get you. You're saying? Okay, I was asking to say, who can tell me the atomic number of oxygen?
Atomic number of atomic mass.
Oxygen.
Atomic number of oxygen is 8.
Is 8.
Yes.
Okay, so how about the proton number? Anyone? I'd illustrated how to find the proton number, and we have the information here on the screen. So just trying to see if we understood what I've explained earlier. The atomic, the proton number. Okay. The atomic mass number of oxygen.
Atomic mass number is equals to number of protons and neutrons.
Yes.
Then, what was your question?
The atomic mass number of oxygen. Not the definition, but the figure. Okay, so it's actually simple. It's what you're seeing on the screen. This is the atomic mass number of oxygen. So when you round this off, it's 16. So let me not confuse you. This is just 16. So like I'd say, the number of protons. Here, let me take you back. Proton number plus neutrons number is equal to atomic mass number. So the atomic mass number of oxygen, is 16, for instance, or 15.9, but that's 16 round. Is 16. So 16 minus 16 is our atomic mass number. Yes. So number of protons is 8. Then we have the number of neutrons, not, which is 8 again. So here they asked two things: the atomic number 8, which you answered correctly. Atomic mass number, we have it at 16. Then the number of neutrons. Remember how I said how you can find the number of neutrons. You subtract from the atomic mass number. You subtract protons from the atomic mass number to find the neutrons. So who can tell me the number of neutrons of oxygen? We have the atomic mass number of 16 and we have the proton number of 8.
So the number of neutrons would be 15.9 minus 8, which is 7.99.
Thank you. Thank you very much. I hope we are all following.
Yes.
Thank you. Thank you. So we come to nitrogen. I want a different person to give us the atomic number of nitrogen.
Atomic number of nitrogen.
Atomic number is same as proton number.
Yes.
Yes. So what is the atomic number of oxygen? I mean of nitrogen.
That is 7.007.
Okay, so okay, well, you can just make it easy for yourself. It's actually 7. But thank you. Thank you. And the atomic mass number?
Atomic mass is 14.007.
Okay, can I? Thank you, Mr. Elvis. Can I have another person to tell me the number of neutrons of nitrogen?
The number of neutrons is 7.
How did you find 7, sir?
Okay, 14.007 minus 7. That is 14.007 is the same as 14 when rounded off into a round figure. Then I subtracted 7 from 14.
So the 7, what is the 7 that you're subtracting from? What is it?
The atomic number.
Thank you.
Or the proton number.
Yes, because the atomic number is same as proton number. Thank you. I needed to know that you're understanding what you're subtracting to what before you can get what you're getting.
Okay.
Thank you very much.
Okay, thank you.
So elements, substances that can be broken down into simpler substances. I repeat, that's a definition of elements. Elements, these are substances that can be broken down into simpler substances. Pure substance made of only one type of atom. It's a pure substance only made of one type of atom, not a combination of different atoms. So it's one, so it cannot be split into simpler substances. Represented by 1 or 2 letter symbol. So this is where the periodic table comes in. But before we can go further to check, I would just want everyone to participate with the symbols that we have here. I'm sure we've seen these signs somewhere. So for example, we have what is C as an element on the periodic table. This is a structure symbol for which element?
Which one?
C.
C is carbon.
Thank you. Thank you, Elvis. Okay, another one to tell us, and H.
H is hydrogen.
Okay, can I have a different participant of O? O.
Oxygen.
Thank you. Thank you. A different participant. L.
Aluminium.
Thank you. Thank you. A different participant for FE.
Iron.
Thank you. Thank you. A different participant for HE.
Ilium.
Thank you. Then GA, different participant. I'm waiting. What?
It is
gallium.
gallium.
Oh, thank you. Thank you very much. Thank you very much. Then the second one, PT. PT.
Lead.
PT.
Platinum.
Thank you. Platinum. And the last one. AU. What? You're breaking. I can't get you clearly. The last one. AU. God. Thank you. Thank you. So these are the examples given of pure substances made of only one type of atom. One type of atom. These are the ones you come across. We have carbon, we have hydrogen, we have oxygen, we have aluminum, we have iron, we have helium, we have gallium, we have platinum, we have gold, noble gases, elements. Excuse me. Someone has a question? Are you able to hear me clearly? Okay, I proceed. Are we together?
Yes, we are together.
Thank you, thank you. So, to not confuse the two, you need to be understanding. So, when we talk of elements, we had mentioned substances that can be broken down into simpler substances. Pure substance made of only one type of atom. And examples given were these. To continue mentioning, let's get familiar to these symbols, because when doing those equations, we won't be finding, we won't be finding full letters like gold, oxygen. It's these symbols that will be coming across. So noble gases, elements that can exist alone. Excuse me? Please, Vivian, I don't know if it's a question you want to ask, but please mute your microphone. Thank you. Okay, so noble gases, elements that can exist alone. Elements that can exist alone. Don't combine with other atoms. These are the noble gases. The examples of noble gases here are these. Again, I'll need a few volunteers to tell me what these are. So we have He,
Hello? Helium.
okay? Then, yes, I can get you. Okay,
Neon.
okay, and the last one.
Argon.
Thank you, thank you, thank you. So we proceed. So we're going to talk about sodium, reaction of sodium. Who can tell me the chemical symbol of sodium?
Sodium is Na.
Thank you. Then mercury. Anyone? Hg. Hg. That's for mercury. Okay. So more than 100 elements are known, but only about 2 dozen are common found in living organisms. Okay. I'm going to open just a minute. Okay. Let's see. So isotopes. Who has an idea of what an isotope is? Okay, so an isotope, atoms of the, okay, someone? Someone wanted to give us a
Yes.
course. What is an isotope?
Atoms of the same element.
Okay.
Atoms. Yes.
Atoms of the
Isotopes
same element.
The same atomic number but different mass number.
You're saying isotope are atoms of the same element that have different numbers of neutrons or the same number. What was your definition? I want to get your definition. Okay.
Isotopes
Yes.
are atoms of the same element with the same atomic number but different mass number.
Thank you. That's another definition. Thank you. So here we have simplified the definition. Atoms of the same element that have different mass number of neutrons. For example, one of the examples of isotope is carbon. We have carbon that has the atomic mass number of 14 and the carbon that has the atomic mass number of 12. Both have 6 proton. Both have 6 as the proton number. 6 protons. The carbon 14, carbon 12, carbon 14 has 8 neutrons. Carbon 12 has 6 neutrons. So the two examples they've given us, the example that they've given us of an isotope, we have the carbon 14 and carbon 12, which both have 6 number of protons, but they have different numbers of neutrons and different number of mass number. So from this, you can tell the definition of what an isotope is from this, then from your simple explanation. Knowing very well the elements, the protons, the atoms. So you can say isotopes are atoms of the same element, which is carbon, is the same element, that have different atomic mass number, which is different, 14, or proton number. They both have 6 as proton number. So the number of proton is the same, and it's the same element, but they have different numbers of atomic mass number, and also a different number of neutrons. Carbon 14 has 8 neutrons, carbon 12 has 6 neutrons. Have we all understood what an isotope is from the simple definition? Yes. So proceed. Isotopes are identified by their mass numbers. For example, carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. Each isotope has a different number of neutrons, but has the same. Each isotope has a different number of neutrons, but has the same number of protons. Also, different number of the atomic mass number. This is how you identify an isotope. Here's a question. Before we can answer the question, I wanted to see if there's any way any of us understands this. How are all the isotopes of an element similar? Okay. Yes.
Hello.
Yes. Someone wanted to give us.
Hello.
Yes, we can get you. Yes.
They have same number of protons. Hello. Same number of protons.
Because we have the same number of protons. Interesting. Thank you. So because they have the same number of protons and electrons. Thank you very much. Remember, we said the number of protons is equal to the number of electrons. So the question was, how are all the isotopes of an element similar? Thank you very much for that answer, Miss. Because they have the same number of protons and electrons. This is why the isotopes of an element are similar. All isotopes of an element have the same chemical properties. Because it doesn't matter, it's a carbon 12, it's a carbon 14, it's a carbon 13. They all have the same chemical properties.
Question.
They undergo similar reactions.
Hello, question.
Yes.
Yeah, what if you say they have same elements in them?
Yes.
Will you be wrong?
Isotopes of an element, they have what?
They have same elements in them. Because according to your question, how are all the isotopes similar, then somebody answer by saying they have the same element in them.
Yeah, someone said they have the same number of
Same.
protons. The
Yeah.
question was, how are all of the isotopes of an element similar? Then she said they have the same number of protons. Yes, which
Yeah.
is correct.
Yeah, it's okay.
Yeah. So what is your question?
No, my question has been answered.
Okay, so you don't just end there as protons. Remember, the number of protons is equal to the number of electrons. So when answering this, you have to finish it this way because they have the same number of protons and electrons. So the number of protons, which is 6 in carbon 14, carbon 12, and carbon 13, is the same number of electrons that are there. You understand?
Yes.
Yes, thank you. So they are showing us this is our carbon 14 isotope of carbon 14, radioactive carbon 14. This is the number of electrons. We have 1, 2, 3, 4, 5, 6. And we have the number of protons 1, 2, 3, 4, 5, 6. Similar. Then we have number of neurons. And we know how to find the number of neurons. We have 1, 2, 3, 4, 5, 6, 7, 8. Are we understanding what an isotope is from this structure? This is a carbon 14 they've shown us. Any question from here? This is an atom, and in the middle cell, there is a nucleus. And this is how elements are arranged because of their charges around the nucleus of an atom. Those are the circles they were mentioning and how their movements are constant around this shell. So radioactive isotopes, some isotopes are radioactive, meaning that their nuclei are unstable and break down at a constant rate over time. Some isotopes are radioactive, meaning that their nuclei are unstable and break down at a constant rate over time. Hence, to this point, their chemical reactions and chemical properties are similar as isotopes because their nuclei are unstable and break down at a constant rate over time. Constant rate. It doesn't matter it's a carbon 14, carbon 12, carbon 13. Their nuclei are unstable and break down at a constant rate over time. Although the radiation these isotopes give off can be dangerous, they have important scientific and practical uses. Proceed. So the uses of isotopes. Radioactive isotopes can be used okay. Since we are both looking at this, we'll just have a few volunteers to say a few things. I love it when we are all participating. Yes, someone to tell us one of the uses of radioactive isotopes. You can either tell us what you are saying or any other uses that you already know. Anyone?
Treatment of cancer.
Treatment of cancer. Thank you. What else do we use radioactive isotopes for? So just to clarify on this, treatment of cancer. Those cancer machines, there are radiations in those scannings and stuff. Those machines that are used, the carbon, before I could go deeper, this is how it should be connected. It's not like it's written, radioactive isotopes. So that helps in treatment of cancer. Then it also helps to determine the ages of rocks and fossils. Determine, the ancient findings, of bones, stones, these things would find Homo habilis, the scars, they would measure. These isotopes help in determining how long this bone has been here. You understand? Are we together?
Yes, we are
Yes.
together.
Thank you. They also help to kill bacteria that cause food to spoil. Also, they help as labels or tracers to follow the movement of substances within an organism.
Question.
Thank you. Go ahead.
Hello. Question.
Yes. Yes.
This question that the one of the apps that says that to kill bacteria that cause food to spoil. So my question is, are they being installed in refrigerators?
No. What this point is trying to say, to kill bacteria that cause food to spoil. These radioactive isotopes are also put in food. How would I put this? There are a lot of means to preserve food.
Yeah.
And yes, and they're actually chemicals that are made specifically for that. And some of these are added to some drinks we even drink, certain foods that we get. They're added there so they can be preserved to avoid them going bad or to spoil. The canned food, those kind of foods, those things can stay. You understand?
Yes.
No, did you understand? Not necessarily installing in the fridge. No.
It's okay.
Yes.
Okay, another question.
Yes.
Excuse me, sir. Excuse me, sir.
Yes.
I have a question.
Mhm.
What are the examples of these Excuse me, sir.
Yes.
Have you got my question?
No, you can ask again.
Yeah, my question is this. What are the examples of these radioactive isotopes?
Examples of radioactive isotopes. We have carbon.
Yeah.
We have carbon 12, carbon 14, carbon 13. Here, let me just take you back a little bit. We have 3 of them, carbon, here. So we have, for carbon, we have 3 isotopes in it. And these are the ones we are talking about. So here we are talking about radioactive carbon 14. Then here in general, we are talking about radioactive isotopes and their usage. So just to add more on the question that earlier was asked about how they are added, preservatives.
Yes.
They are formed, yes, radioactive isotopes. They are contained in those preservatives, substances or chemicals that is added to products such as food products, beverages, pharmaceutical drugs. paints, biological samples, cosmetics. So those preservatives contain radioactive isotopes. It is the property, the chemical property, that helps them to kill bacteria. Even these are pesticides. You know, maize would need pesticides, you know, so that we can kill those pests that gets to, you know, eat maize and stuff. You understand?
Yes.
So yes, that's how these radioactive isotopes helps. So there is that content of them in the preservative that is used. We can proceed. Any question, please? I think there was another question.
There's also a question.
Yes.
This point number 4, as labels or traces to follow the movement of substance within an organism. How?
Okay, so let's say, for instance, we'll say an animal, or let's say a mice, because that's what they usually use in labs when they're trying to find out something. So they are used as tracers. When an isotope radioactive is implanted in a human or in an animal to attach to a specific either cell or organ within, or let's say you have worms, right? Or you have something. Let's just say you have a worm. This can be used to track it. Once you are implanted with that, it will be used as a label or tracer. Once it's attached to that, it will be showing how that is moving in that animal or yourself. It's the human body. You understand? So now they say it can be used as labels or tracers to follow the movement of substances within an organism. You understand?
Yeah.
Yes.
So I have a question.
Thank you. Go ahead.
I have a question, sir.
Yes.
There's this.
You're breaking? Hello? Oh, but I don't know if it's the network. You're breaking. Please try to ask again. Or did anyone ask, understand the question he was trying to ask? Okay, so we proceed. We are together?
Yes, we are together.
All right. So chemical compounds. Chemical compounds. In nature, most elements are found combined with other elements in compounds. A chemical compound is a substance formed by the chemical combination of two or more elements in definite proportions. I'll repeat the definition of a chemical compound. A chemical compound is a substance formed by the chemical combination of two or more elements in definite proportion. Excuse me, I can hear a voice. Trying to ask a question? Ask the question? Yes, please. Hello, shall we proceed? So a chemical compound is a substance formed by the chemical combination of two or more elements in definite proportions. The physical and chemical properties of a compound are different from the elements from which it is formed. I don't know if you understand this last point. What they are saying is that a chemical compound is a substance formed by the chemical combination of two or more elements. Two or more elements. They combine together in definite or definite proportions. That is what is called a chemical compound. So the physical and chemical properties of a compound are different from the elements from which it is formed. So the physical and chemical properties of a compound are different from those substances that are involved to form that compound. They do not undergo the same properties because there's been a combination of two or more different substances to form that chemical compound. So the physical and chemical properties of the compound are different from the elements from which it is formed. They're together?
Yes.
Yes. So chemical compounds. Scientists show the composition of compounds by a kind of shorthand known as molecular formula. That's a chemical compound. So scientists show the composition of compounds by a kind of shorthand known as molecular formula. We all understand what the molecular formula is, isn't it? This is a formula that is given to a compound, showing briefly the combination or the elements or substances that are involved in that chemical compound. So for example, we have water. We know water is a combination of hydrogen and oxygen, and this is its molecular formula. Are we looking at that?
Yes.
Yes. Water is a chemical compound. It's a combination of hydrogen and oxygen. It contains two atoms of hydrogen for each atom of oxygen. They're explaining from the definition. We say substance formed by the chemical combination of two or more elements in definite proportion. Indefinite proportion. This point from here, just indefinite proportions, is exactly what they're trying to explain, how these are combined. So we have hydrogen and oxygen. How do these bonds? Yes, please. Yes, please. Oh, the network is really bad. Okay, for those that are having a hard time, you can type the question, and if I see a notification here, I try to read it in the chat or Zoom chat because I can hardly get you. Okay, sir. So try. I think your network is really bad. I don't know if it's the network. So you can try just to type the question in the chat. I'll try to view it and answer it. I think that will help because I've actually noticed you are struggling to participate due to the network. You post it in the chat so that everyone can see the question and we can answer it properly. Okay, so we proceed. So the definite combination, the definite proportion, the combination of these elements. Water, which is H2O, contains two atoms of hydrogen for each atom of oxygen. For each atom of oxygen, there's two atoms of hydrogen for each atom of oxygen. This is one of our chemical compounds. Another chemical compound is the commonly known salt, the formula for table salt. The salt that is usually used, sodium chloride. So this is a salt. There's sodium and there's chlorine. We are together.
Yes.
Did anyone have questions on the water? I will explain it. You understood? Anyone? Any question? The chemical compound, which is water. Okay, so we proceed. So the formula for table salt. Here we have sodium and chlorine, which is sodium chloride. So sodium chlorine indicates that sodium and chlorine combine in a 1-to-1 ratio. 1-to-1 ratio. Sodium and chlorine. We don't have atoms like two atoms. Excuse me? Yes, please. I can't get you. I can just get that someone is trying to ask a question. Okay, I proceed. So the formula for table salt, which is sodium chloride. Sodium, it indicates that sodium and chlorine combine in 1-to-1 ratio. Unlike the way water, chemical compound, is made of hydrogen and oxygen, showing that 2 atoms of hydrogen for each atom of oxygen. There's a 2 there, but when you look at sodium chloride, there is no atom number showing anywhere. So it means the combination of these 2 is in a ratio of 1-to-1 ratio. So molecular formulas shows numbers of molecules in atoms. I don't know if it's just the bad feedback or this person is still trying to ask a question. Okay, so molecular formulas shows numbers of molecules and atoms. Molecules is equal to coefficient, the number in front of the molecule, of the molecular formula. For example, here, 3 hydrogen, 2, 0 is equal to 2. How this is made is involved when balancing this equation. So we'll understand this later as we go now. But now let's just pay attention to how this is moving the points. Atoms is equal to number of atoms of a compound. So, for example, oxygen, hydrogen, water here, H2O is equal to 2 hydrogens, 1 oxygen, 1 oxygen is the total of 3 atoms in this compound. So the number yes. Yes, please. Okay, we are just winding up. We need to finish up our time is almost out. we get you there. So let's do this. Okay, so I think the next time we meet in chemistry, I'll explain properly on this. Still on the formulas, so we can proceed. Structure formula, where we do the isomers, NHLs, mixture and configurations, valency, there. Okay. So I think chemistry and got carried away. I didn't even check my time. Okay, so we have introduced chemistry and we've done at least the basic and foundations of chemistry. We've done atoms, isotopes, chemical compounds, which we started. Also done the elements, practice, atoms. Okay, so continue next time in chemistry. We just want to wind up and conclude biology. We're still on cell and we ended on mitochondria. Am I right? Because we can remember.
Hello.
Hello? Yes?
Yeah, just to confirm.
Yes, please.
Yeah, we are getting you from far.
Oh, you're getting me from far?
Yeah.
Sorry.
But let's do
How about
something.
this?
Eh?
How about this? How clear am I?
Now it's a bit nearer.
Okay.
Then another concern.
Yes, please.
You just please, please, if you get free time, just send the slides to our director. At least we get the notes.
The notes.
Yeah.
Okay. So I think this should be the suggestion. Do you have a group? Or we can come up. You have a group?
Yeah.
Okay, so this is what we're going to do. Okay, we'll do this. I'll communicate to I'll communicate to Mr. Evans.
Yeah.
Yes. And you have these notes posted in the group. So as we meet, you all took your time to go through, revise and stuff. Is that okay?
It's okay.
All right. So yeah, jumping on to biology.
Hello, sir.
Yes, I'm still.
Yeah, you are requesting for a short break. Then we come back, if you don't mind.
Yes, I was just actually checking. So this can be recorded and posted. Sure. So we'll have a short break of how many minutes do you think?